So section 3.2 is going to talk about algorithms for whole number addition and subtraction. Algorithms just means ways we do these things. It's the way in which we do something, all right? Sort of like the step-by-step process, the process by which we add or the process by which we subtract. We're going to take a look at the concrete model first. And when we look at a concrete model, we're talking about the early stages that children would go through with things like blocks. You could do it with money. It doesn't have to necessarily be blocks, but blocks are the ones that we tend to draw the most frequently with these. So this would be the idea that we could represent the number 34 as, let me get me a rectangle here, as 3 longs. Okay, so 3 of these pieces that are long, and we've talked about these in the last section, right? The longs, didn't we? I'm not making that up, am I? Okay, good. I'm glad that I talked about that once before, my goodness. And then we'd had 4 of the little units. Okay, so that's 34. And then we can talk about having 18, and so 18 would be 1 of these longs, and then 8 units. Okay, so we're combining these sort of into a single quantity. And if you count them as they are right now, how many longs do you have? 4. And how many units do you have? 12. But we don't want to have 12 units because that's more little bitty blocks than we need. We can actually trade some of those little unit blocks in for a long. How many unit blocks would we need to trade in? 10. So we can take 10 of these guys. So there's these 8 right here. And we can take 2 more of them, say, and we can turn them into a long. So we can change this from having 4 longs to having 1, 2, 3, 4, 5 longs, and then what else? 2 units. And there's absolutely no reason why this is bigger except that I was figuring out that my drawing was so small I was having difficulty doing it. So there's not like the answer should be bigger than the other ones or anything like that. And if we look at this and we count, what number is this? 52. So this is a concrete model. Obviously, you don't want children to do this for very long because this is going to take a lot of paper. It's going to take a lot of time to draw the pictures. But in terms of actually working with concrete items, it's a really good place to start. Okay, and then again, there's nothing special about these units or these values. We could have used coins the same way, right? I could use dimes in place of the longs, and I could use pennies in place of the units, and that would work too. Right? So I have 10 pennies and it becomes a dime and so forth. Make sense? Okay, so this is a concrete model. The others are going to work a little bit differently. They're not going to have pictures. The next one's called the expanded algorithm. And the expanded algorithm has a couple of forms I'm going to show you. First, the expanded algorithm could take on the look like this. When we talk about the number 34, we mean 3 times 10 plus 4 times 1. Agreed? That's what 34 means in expanded form. We could do the same thing with the number 18. This is 1 times 10 plus 8 times 1. And we can add these together, just again like we did with the picture. We're going to get the same answer. Okay, so no surprises, right? 3 plus 1, and we can work from left to right. 3 plus 1 is 4. So this is 4 times 10 and 12 times 1. But then we, of course, have to recognize that I don't have, excuse me, I don't have 12 times 1. I don't want to have that many ones. So I can separate this so that it becomes 4 times 10 plus 1 times 10 plus 2 times 1. So I separated out the 12 times 1 into 1 times 10 and 2 times 1. 1 10 and 2 ones, 1 dime and 2 pennies. And then I can combine the pieces that go together again as you're taking a look. So this is 5 times 10 plus 2 times 1, which is 52. Sorry, yeah, which is 52. This is one way of drawing the expanded algorithm. I'd like to show you another way to do the expanded algorithm as well. The second option I'm going to show you, they don't show this in your book, but I've seen it used in another book, and I think it's a helpful view too. So another way to think about this is to think about doing it one at a time. So the 3 is actually representing 30, and the 1 is actually representing the number 10. This is 30 plus 10. So what's 30 plus 10? 40. And then I have 4 plus 8. And what is 4 plus 8? 12. The nice thing about this is that you're actually adding the values together as they really are. And then 40 plus 12 is actually going to give me the 52. So you're sort of adding like values together, but you're actually expressing them in terms of what they really are. In other words, when I add the 3 and the 1 right here, I'm really not adding 3 plus 1. I'm really adding 30 plus 10. That's what's really going on in the problem. And so this actually explicitly writes it out in that fashion. Okay, I'm going to do the standard algorithm, although I know you guys know this one, and it works very efficiently. Efficient means it's quick. Okay, it's very efficient, it's very quick. Effective, maybe, maybe not. Probably depends on the person who's working with it, but it's the one that you're most familiar with using. So you guys walk me through it. What do you do normally as you have learned to do 34 plus 18? You do the 4 plus 8. So what is 4 plus 8? 12. So what do I do with the number 12, Taylor? Okay, so let's stop for a moment and let's talk about what in the world we just did. The number 12 got written with a 2 below and I carried a 1. Why? What's the 1's place? The 2 is in the 1's place. Why did I carry the 1? Because what does that 1 actually represent? That 1 in the number 12 represents a 10. That's why we carried the 1. We carried the 1 because it was 110. Not 110, but it was single unit 1 with a value of 10. So now I've got all the 10s lined up. I've got the 10 that I carried. That was the number 1 at the top. I've got a 3 that's already there, and I've got the 1 below. So then I'm able to add the 1, the 3, and the 1 because they're all 10s, right? And that gives me the number 5. So pause for a moment because I know you guys are familiar and comfortable with this, and so some of you I know are thinking it, whether you're willing to say it out loud or not. What's wrong with this? I mean, right? We've been doing it forever this way. You're very comfortable with it. What kinds of things could cause kids sort of confusion or problems or issues with what's going on when we do it in this way? It doesn't make it wrong, it just makes it something that you need to think about. What could they confuse about doing it this way?
They could make the 1 look like a 13.
They could. They could take that number 1 that we put at the top and make that 1 sort of look like I've got the number 13 instead. Okay, that's legitimate. What else?
You don't explain about the 1 being a 10, and they just assume, like, they don't understand the concept of adding 10 to it.
Yeah, I think that can be really confusing. In fact, some of you, as I was looking at this, I know you've probably never thought about what you just did when you did it before. You verbalized it pretty well. But what in the world happens? What does that 1 carrying over look like? Because it kind of looks a little bit like magic. Doesn't it? I mean, we just sort of like, we put it somewhere. Oh, let's just put it on top of the 3. I mean, what? Well, there's a reason for it, right? But if we're not explaining what the reason for it is, it can look pretty obscure. Katrina, was that what you were thinking? Yeah, I mean, it looks a little bit funny. There's something else here that's a little bit awkward that you haven't caught on to yet.
You might try from the left to right.
That's right, Katrina. So how do you guys read?
Left to right.
From left to right. And how did we just do this problem?
Right to left.
That seems a little weird, doesn't it? We did the math problem from right to left. In fact, we do most of our math problems, though not all of them, from right to left. And that's a little bit weird. So that can feel a little bit awkward. And if a child's not being careful, and they did move from left to right because that's how you read, you could run into some problems as well, right? You can add the 3 and the 1, and then it comes up with 4, and then you add the 4 and the 8, and all of a sudden you have 12. But if you're not careful, the number might end up looking like this. Do you see why? If you just write the number 3 plus 1 and it's 4, and you write down 4 plus 8 and it's 12, well, that's the number 412. That's how we read. So it's not that the method that we've used for so long is wrong or bad. It's just that it requires a little bit more thought behind it than you've probably thought about in a while. And some kids are going to have some problems if you're not aware of what kinds of errors you might expect them to be making. Okay? All right. So we're going to look at left to right. A left to right algorithm then. How would it be done if it's done properly? Because I just showed you how to do it sort of done in an awkward way that didn't work, right? So let's take a look at how we could do it from left to right, the way that we read, but do it and make it work. Okay, so here's what we do. We're going to recognize that when we add the 1 and the 3, we do in fact get a 4. But we're going to recognize that that 1 is the number 1,000 and that 3 is the number 3,000. So when I add them together, I actually get 4,000. Everybody good with that? Look okay? Now, I'll address an issue with this in a little bit, but let's continue first. Now I'm going to add the number 5 and the number 2, so I'm going to get the number 7. But that's really 500 plus 200, so it's really the number 700. This 3 here is the number 30, and the 1 is the number 10, so this is the number 40. And then we have that same 4 and 8 that we had a minute ago, but what is 4 and 8? It's 12. But when we're writing it out in this way, we get them lined up properly, right? We don't have the 12, all of it in the ones column, which is where I was leading us into the other sort of misconception. Once you've gotten it into this sort of a view, you can actually add left to right or right to left, and you won't have any error, you won't have any rounding problems going on because of the way that we've done it step by step with the different place values one at a time. So this actually gives you the 4, the 7. I've got 4 plus 1, that's 5, and then the 2, and I can actually work from left to right completely. So this sort of fixes the place value issue that I said could come into play when I got the 412 just a minute ago. The thing about this that's maybe not quite so friendly or helpful is that it's not terribly efficient. Okay, so efficient means it's quick, quick to do. There's lots of things I just wrote down. It's not terribly efficient, but it definitely is correct, right? It's effective. It still works. And it does eliminate a possibility of this weird left to right, right to left business going on. And it eliminates the ability that if somebody is going to try to move from left to right, that they're going to end up with place values not aligned correctly. Okay? All right, let me show you another one. Lattice algorithm is a different one. It is very interesting. And so who's had contemporary math in here? Okay, did you guys do lattice algorithm for multiplication there? Yeah? Okay, this is sort of akin to that. It's going to look a little bit different, though. So we're actually going to write out the number 18943218, just like if we were writing it with the standard algorithm or even that left to right algorithm we just did. And underneath it, we're going to draw sort of a rectangular box. And our box needs to have a placeholder for every placeholder in the add-ins. So I have 4 place values in the add-ins. Each of those had 4 values, so I'm going to have 4 placeholders in this box. Then I'm going to draw the box with diagonals cutting them in half, each of the boxes. You can move from left to right or right to left, doesn't matter at all in this particular algorithm, so I'm just going to go from left to right because that's how I read. 1 plus 3 is 4. And so you write the 4 underneath that in that box. The ones column or the ones place is the lower half of the box. If it had a tens in it, it would be the upper half of the box. And we'll get to one of those in a minute. 8 plus 2 is 10. So I'd have the number 1 and then 0. So 1 goes in the top half of the box and the 0 goes in the bottom half of the box. 9 and 1 is 10 again, so top half, bottom half. And then 4 and 8 is 12, so I have the top half, the bottom half. Okay, so that sounds like great, but now I've got this weird looking box thing going on, and that certainly doesn't look like the answer I was expecting, so what do I do next? Well, what you do next is where it mirrors what happens with lattice multiplication, and for those of you who don't know what I'm talking about, we'll get there in a couple sections. Those diagonals are actually the place values. Okay? We do need to start at the bottom diagonal. Okay? So that's where our number 2 is here. So this number is 2. We look at the next diagonal over. I've got a 1 in the top right and a 0 on the bottom left, and we add them together to give me a 1. Okay? Next diagonal over, 1 in the top right, 0 on the bottom left. So that's to add up to the number 1. Third diagonal over, 1 on the top right, I keep saying the wrong word, 1 on the top right, 4 on the bottom left, and 1 and 4 is 5. So the solution, the answer is 5,112. So you add along the diagonals. So what this lattice method does is it allows you to do the addition and to keep things in the correct place value. So in other words, when I put that 1 in that top corner over here with the number 12, when this 1 went up here, this is the tens column. It just doesn't look like it because it's drawn on a diagonal. Okay? So I'm getting the tens column from adding the 1 and the 4 and the 8 together, and the 0 beneath it is actually the tens column from having added the 9 and the 1 above it and getting the number 10. I had 1 of these and 0 tens because I was actually adding 90 and 10 together to give me the number 100. Okay? So this splits up the place values in just a little bit different way. Do I have one more? Oh yes, there's one more. The next one here is called Scratch Algorithm. And Scratch Algorithm is not something you would just randomly use for any list of numbers. However, or any sum of numbers. However, it works really well when you're adding several numbers together. So you see here I'm actually looking at adding 4 numbers together, right? Not like 2 4-digit numbers like the last 2 problems I did. So this method works very nicely when you're adding a list of numbers together. So 34, 18, 69, and 87, and you're adding them all together. So here's how it works. We are moving from right to left, okay? So we're going to start with the 4, 8, 9, 7 on the right-hand column, the ones column. We're going to start at the top. What is 4 plus 8? 12. What we're going to do anytime we hit the number 10 is we're going to scratch out that number, and we're going to remember the ones digit. So in the number 12, what is the ones digit? A 2. Okay, so I'm going to ignore the fact that this previously was 12. The scratch took care of the fact that it was 12. I'll show you what we do with the scratch in a minute. We're going to remember the number 2. Now I'm going to take the number 2 and I'm going to add it to the number 9. What's 2 plus 9? 11, which is bigger than 10 again, right? So I'm going to scratch again. The number 11, what's the ones place in the number 11? 1. So I'm going to remember 1. I'm going to add 1 plus the 7, which is going to give me 8. Count your scratches. How many scratches did we have? 2 scratches. And the reason we had 2 scratches is because those were the 2 times when we exceeded the value 10. So I'm carrying 2 tens over, because that's what those scratches represented. The scratches represented getting a 10. So we're going to do the same thing again. 2 plus 3 is 5 plus 1 is 6 plus 6 is 12. That's more than 10. So I scratch the 6. The number 12 has a 2 in the ones place, so I remember the number 2. 2 plus 8 is 10, so I scratch. What number is in the ones place in the number 10? 0, so I write down that final result of 0. How many scratches did I have? 2. So I carry the 2 over. There's nothing in the hundreds column right now to add that to 2, so it's a 208, and you bring it down. This is one of my favorite methods. It feels really awkward at first, so I know some of you are going, favorite method, what is her problem? I'm okay with that. But let me tell you the benefit for doing this particular method. Number 1, it really doesn't do you any good at all unless you've got a list of numbers. Okay, so if you're just adding 2 numbers together, scratch addition doesn't even make any sense. Okay, so if this is for a list of long numbers or a long list of numbers. But let me think you think with me for a moment what you would have done if you'd been given this list and you added it sort of in the way that we did without the scratch addition. You would have said 4 plus 8 is 12, and then you'd have to do 12 plus 9, which you may have learned flashcards for, but you also might not have. 12 plus 9 is going to be 21, and then you're going to have to say 21 plus 7, which is going to give you 28. But I know you did not have a flashcard for 21 plus 7, ever. Are you guys following with me? The benefit to scratch addition is that it reduces all the addition that you're doing back to the flashcard addition that most kids probably have memorized somewhere along the way. It changes all the values so that you don't end up adding larger values to a smaller value in there. And for some kids, that's really important. I have had students in this class grab a calculator to add some of these numbers together before. Okay? Some of you guys just don't have the same background, right? You don't have the memorization background, and if you add the numbers that are 2-digit number to something else, you just look at me like I asked you to do something that was like trigonometry or something. I didn't, okay? But it's just the place where you have been. So what this does is it allows you to turn all the addition into flashcard addition. That's what it does. And that's actually really nice for a lot of kids. Okay? So this is scratch addition. Subtraction algorithms. All right. All right, I'm going to show you the 3 subtraction algorithms, and that's where we'll stop for today. All right, subtraction algorithms. Concrete model. That's the one with pictures, right? So we did this values before where we did 34 and 18. So here's the way it works, though. I'm going to start with the 34. So here's 1, 2, 3. And then I've got my 4 individual units. There's 34. Basically, I've got a group of 34 blocks. And if you were here last time, we talked about different ways to think about it. One of the ways to talk about subtraction is take away. I have 34 and I take away 18. Well, 18 is easy to take away that 1 in the number 18. I just take away 1 long. But I'm supposed to take away 8 units, and I don't have 8 units to take away, do I? I only have 4 little units to take away. So what do you have to do when you take away, in order to take away 8 units? Yes, I need to take one of my longs, and I need to turn one of my longs into 10 single units. So I'm going to rewrite this the way that it's going to actually be able to be solved from. I'm going to only have 2 longs now. There's the original 4. And there's my 10. Okay, so these 10 little units right here came from taking one of the longs and turning it into 10 units. Right? This is what you do when you do change, like when you count money back, right? You could do this with coins just as well as with blocks. So again, this is equivalent to what I had before. Now I need to take this picture, I need to remove 18 of them. So in order to take away 18 then, I would take away 1 long and what else? 8 blocks. So here's 4 blocks all removed. I'll circle 4 more blocks all removed. What in the world am I left with? 1 long and what else? 6 blocks, 6 units. And what does that give me? 16, thank you. So I have the number 16 when I do the subtraction instead. Again, from a concrete model, hands-on perspective, something we don't want to do forever, but when we're first learning addition and subtraction, it's really handy to talk about it. And in fact, it's really handy when you start taking a look at what we do when we do something called borrowing in the standard model. So we'll come back to this idea of what we just did in that concrete model when we do the standard model. When we talk about the expanded model, we saw the expanded model a little bit ago with addition. Works very much the same way here for subtraction. I have 3 times 10 plus 4 times 1. And then I have 1 times 10 for the 18. And then I have the 8 times 1 for the 8 part of the 18. And I'm supposed to be subtracting this last one, in fact. So this is actually minus this and minus this, right? So I'm perfectly fine with doing 3 minus 1, that gives me 2. The problem, of course, is that I can't do 4 minus 8, right? So what we literally did just a moment ago is we took one of our 10s and we changed it in for 10 ones. So we took this and we said, okay, I'm only going to have 2 10s and I'm going to have an addition. In fact, I'll do an in-between step to remind us here. And I'm turning this into 10 ones, so it's 10 times 1, plus the original 4 times 1. All right, that's what I'm doing here. In fact, let me do it. I'm going to put this piece over here. That's how we're thinking about it. So what I actually end up with then is I have 2 10s and how many ones? Right, 10 here and 4 here, so 14 ones. And then it makes sense to take away 1 10 and to take away 8 ones. So what is 2 minus 1? 1, so I've got 1 10 left over. And what is 14 minus 8? 6. There's 6 ones left over, and I have the number 16. Let me show you, again, this is sort of an aside, another way of doing the expanded model, kind of like I did in the last with the addition. If I do this with 34 minus 18, remember if I, no, here, and I want to move left to right a little bit, I can actually talk about this being 30 minus 10, and I can talk about this being 4 minus 8. Depending on what level the kids are at or how comfortable they are with looking at these in terms of negative numbers, you can also think about it like this. 30 minus 10 is 20. 4 minus 8 is what? I know this moves us outside of whole numbers, which is why it's not in your book. But what is 4 minus 8? It's negative 4. And then what's 20 minus 4? 16. So if you've got kids who are comfortable with the idea of numbers being able to be negative, and some of them will be, this is another view of how to think about it that also works. Now let's talk about standard algorithm, the standard model. If you're doing 34 minus 18 here, we start from the right-hand side and we say 4 minus 8, and we say I can't take away 8 from 4, right? No negatives, none of that. So we have to do something called borrowing. And so when we do borrowing, it does like this, and we say, oh, the 3 becomes a 2, and sometimes people will just do this, and they'll put this number 1 in here, funny looking like that. What they would be better, at the very least, to do is to take the 4 and make the 4 become a 14. So let's talk about what in the world we just did. What in the world did we do to make the 3 become a 2 and the 4 become a 14?
Took the 10 away.
We took the 10 and we turned it into we turned it into 10 ones, right? And with the number 4 that was already there, that's the 14. So that's why it happened. But again, without a little bit of explanation, it sort of looks funny. Looks a little bit like magic, right? But it does give me the values that I need in order to subtract. Then I can actually take the 14 minus the 8 to give me 6. And I can take the 2 minus the 1 to give me 1. All right, there's one more method. I think this is the last one before we're going to pause for today. And this is called equal additions algorithm. The whole goal in this algorithm, write this down, the whole goal in this algorithm is to avoid borrowing. Okay? Whole goal is to avoid borrowing. So right now, if you were to do this, you would have to do 4 minus 8 and you'd have to borrow. Agreed? Okay, so we're going to avoid borrowing, and here's how we're going to do this. We are going to take the number 158 and we're going to add 2 to it. Why would we add 2 to 158? Because that makes the number 160, and I like subtracting zeros, don't you? I definitely don't have to borrow if I have to subtract a 0. But if I add 2 to the bottom number, I have to add to the top number, so now I have 836. So 836 minus 160, that was just, my handwriting is awful today. It's a little bit better. All right, so 6 minus 0, we're good with that, right? No borrowing in the ones place. But what happens when you move to the tens place? You've got a 3 minus 6. Also, no good. I can't do 3 minus 6. That would involve borrowing. So what could I add to the 6 to turn it into a 0? 4. But that's not really the number 4. It's the number 40 because it's in the tens column. If I add 40 to the bottom number, I would be adding 40 to the top number. So the number 160 plus 40 on the bottom becomes the number 200. The number 836 plus 40 becomes the number 876. Can you now subtract without borrowing? Absolutely can. So 876 minus 200 would be the number 676. And I know this sounds really funny, but this is actually one that came across on, oddly enough, on Facebook the other day. My husband said that one of his friends, it's a friend from a while back, said, this is how he thinks about math. And my husband thought it was the dumbest thing he'd ever heard. I could tell just by the way he said it to me. And I was like, I teach that, Jeff. He kind of laughed, and he was like, okay, all right then. The thing is, you don't know how your students are going to think about it. And if you don't like this, I don't really care. I don't have to like it either. But there's some kid for whom this is going to be, that's the way they think. And that's really good because that means that you've been able to teach them in a way that they can actually make sense of it. Okay? So this is an additional method for doing this.